Hello everyone, let me introduce myself. My name is Muhammad Faiz Dzulfiqar. Now I'm currently enrolled as a mechanical engineering student at Sebelas University in Indonesia. In this session, I will explain my last research assessment on the design and structural frame of the automatic thickness checking machine, numerical validation in FE method. This presentation will be divided into 5 chapters. The first chapter, Introduction. Next, in the second chapter, the literature review. The third chapter is about research method. Chapter 4, results and discussion. And the last chapter, conclusion and recommendation for further related subject research. Okay, in the first chapter, introduction. In an era of rapidly emerging product innovation, quality control is one of the critical processes in engineering. Hence, manufacturers are facing a challenge to improve production performance to sustain their competitive advantages and maximizing profit. There are three main fundamental functions that have significant impacts on production performance. These are production control, maintenance, scheduling, and quality control. Thickness measurement has an essential role in brake pad manufacture. An example of thickness measurement in the industry is in Akebono Brake Astra Indonesia, in their quality control department that use the ultrasonic thickness gauge operated by a man to check the specimen one by one. The next chapter is the literature review to quantify the finite element result. In this chapter, we will discuss von Mises stress, factor of safety, and displacement. The next is von Mises stress. For the ductile material, failure is considered to occur at the onset of plastic deformation. The uniqueness of failure or stress measurement is that the failure theories which apply for ductile material does not applicable for brittle material and vice versa. Tresca and von Mises method are applicable to ductile material. Both methods agree well with experimental observation, although von Mises agrees slightly better. In the figure of plane stress yield surface, it is shown that the Tresca yield surface lies entirely inside the von Mises surface, meaning the Tresca is more conservative. A factor of safety is the load carrying capacity of a system beyond what the system actually supports, like bridges, buildings, safety equipment, and fall protection all start with a safety factor. The factor of safety is the backbone of all structure and system equipment. In the planning phase of all structure and safety equipment, it is required to determine overload from any object to remain safe in the event of emergency. Safety factor can be expressed as a ratio that compares absolute strength to actual applied load, or it may be expressed as a constant value that a structure must meet or exceed according to law, specification, contract, or standard. So then, why is the safety factor important? Factors of safety increase the safety of people and reduce the risk of failure of a product. When it comes to safety equipment and fall protection, the factor of safety is extremely important. If a structure fails, there is a risk of injury and death as well as a company's financial loss. The safety factor is higher when there is a possibility that a failure will result in these things. Okay, the next is displacement. Beams are used to carry load in a label range of different structure, and it is important to predict how much a beam will deflect when loads are applied to it. Allow a beam to deflect too much and it could cause damage to other parts of structure, feel unsafe to the user, and fail to meet the intended function. There are a few different approaches that can be used to do this. Currently, there are 5 common methods to evaluate the deflection of a beam: double integration method, Michaelis method, moment area method, superposition method, and Castigliano's theorem. All of these methods make the same important assumption, which is that the deflections are small and stresses remain in the elastic region. On the third chapter, research method, we will discuss the geometrical model and the material and FE setting. The automatic text checking machine in this paper was designed using Festo linear drive as its driving motion system with overhead crane arrangement is applied as its structure model. The x-axis of overhead crane arrangement must have two support points over its y-axis. In this paper, the x-axis was set up using the Festo linear drive 600 mm strokes so that it can support the measurement of multiple brake pads in a row. The y-axis was set up using Festo linear drive 100 mm for the motorized drive, as it can accommodate the measurement of the length of brake pads. Furthermore, the y-axis also used the Festo linear drive 200 mm as supporting device for the x-axis. The z-axis on this design was designed using another linear drive series as before because it should accommodate a vertical movement. Thus, this axis uses Festo mini slides series as it can perform telescopic movement. Assembly setting between x-axis and y-axis component were connected axially with two Festo adapter kit. The model was designed using the same Festo motor, Festo parallel kit, and Festo adapter kit. The price aspect of each component had an important role in obtaining a relatively cheap machine compared to another machine that has function similarity. Aside from the price aspect, the quality aspect remained the most crucial outlook on any machine. Therefore, the moving parts object in this design using Festo parts known for their excellent quality. The estimation price of each component is presented in a table, which disclose the Festo parts significantly impact the total estimation price. The estimation of the total price of the structure is 4,500 euros. This price estimation is relatively cheaper than other automatic thickness checking machine. Thus, this machine can be produced and help the company to check brake pads rapidly and efficiently. In the material and FE setting, the automatic thickness checking machine uses 6061 aluminum type. The use of this material is considered on availability on the market, and this material can be easily found. The square hollow aluminum frame has a square shape of 25 mm width and length size. The thickness of the frame is evenly 1 mm on each side, so then the width and length on the inner side are 23 mm. The material properties that is shown in the table were taken from Autodesk Fusion 360 library, which later used on finite element analysis simulation. In view of the selling price, this material will cost relatively cheap and not as expensive as the slot aluminum frame. And the frame connector is made from ABS plastic, and it is needed to assemble the aluminum frame to stand rigidly. Okay, the next discussion in material and FE setting. The applied force type on finite element analysis has a significant result in the simulation. That is why every force, load, and moment that occurred on the structure must be determined conscientiously. The finite element method determination of the structure of automatic thickness checking machine is supported on 4 points constraint located in the base sectional area of the aluminum profile. Constraints are applied to a model to prevent it from moving in response to applied loads and add constraints to mimic environmental conditions. The loading type applied in the simulation are all distributed load on the top side of the frame and on the top side of the frame slider. On the top side, 50 Newton forces are applied on one bracket, then the total force applied on four brackets are 200 Newton. On the frame slider, 40 Newton force are applied on its top side, then the entire force applied on two frame slider are 80 Newton. Okay, so in chapter 4 we will discuss the result that were quantified on three subjects: von Mises stress, factor of safety, and displacement. The von Mises stress simulation result shows the highest result is 29.86 megapascal, and the minimum of value is 2.275 times 10 to the minus 5 megapascal. The highest result have primarily occurred on the top aluminum profile, frame of the structure of the automatic thickness checking machine. In this area, the structure is given a constant load of the Festo assembly mechanism and the ultrasonic thickness gauge. Furthermore, the maximum value is in the middle because it is the midpoint of two load points. At the same time, the minimum von Mises stress occurred is on the upper backside of the frame. Okay, next is factor of safety. The structure of the automatic thickness checking machine is subjected to the load of the moving mechanism structure made of Festo component assembly. These components have the basic mass and the moving mass. This research was conducted by calculating the total possible mass. An object is safe if the minimum value of safety factor is 1. As presented in the figure, it indicates that the structure of the aluminum thickness checking machine is safe because the safety factor is reached more than 1. The minimum factor of safety is 3.362 and the maximum safety factor is 15, which was located on the beam with the least forces affected by the given load. A deflection on a beam with a direction perpendicular to its axis is caused by the bending load applied to a beam. As shown in the displacement contour, the red area on the structure of the automatic checking machine have the most considerable deflection that occurred by the given static load. The red area is located on the right upper side of the frame, and this is caused by the beam has two forces applied on it, and the distance of two loads is shorter than the load's distance on the upper left side of the structure. Nonetheless, the deflecting amount is really small, so that the deflection is not affecting the structure much. The minimum displacement in this configuration is 0 and the maximum is 0.06475 mm. Okay, now we're in the last chapter, conclusion. In this chapter, we will discuss the concluding remarks and recommendation for further work. From this research, it can be concluded as here. First, square hollow aluminum 6061 frame is viable for structure. And second, the result has von Mises maximum stress 29.86 megapascal and a minimum of 2.275 times 10^-5 megapascal. And the third, the maximum safety factor is at 15 and the minimum at 3.362. Fourth, the maximum magnitude displacement is 0.06475 mm. And the last one, price aspect as one of the major outlook of industrial products. The recommendation from this research is comparing other material or different geometrical component structure to know the better result compared by the price aspect. That's all from me. Thank you for your attention.